Hello, my name is Gennady Malaschonok. I am from the University of National University Kyiv-Mohyla Academy, it's Kyiv, Ukraine. And the title of my talk is LSU factorization, some kind of LU factorization. First of all, I want to thank the organizer for the possibility to give this talk. And I want to thank to the company of Genesis. He paid the organization fee for my participation in the conference. The outline of my presentation is next. We have two parts. The first part is algorithm in the field, LU, VWU, LU, and the second part is algorithm in the domain of the U and LSU. The main part of my talk is LSU factorization. Everybody knows the LU factorization and the case of PLUQ, where P and Q is a matrix of permutations. It is an example. If you have matrix A, then L is a low triangular matrix, the U is upper triangular matrix, and P is a matrix of permutation. And the product PLU is equal A. This is classical factorization, which is one of the most popular program at the supercomputer. And we can check that it's indeed, if you compute such product and A subtract PLU, we obtain R. R is a zero matrix, and we can check it. Is it zero? Yes. Another variant is Breuer decomposition. First time Breuer decomposition was first who used such decomposition was Breuer. It was 1954. What is difference? Here it is V and U is triangular matrix, and W is the matrix of permutation. This is an example. And in this case, V and U, it is an upper triangular matrix. It is very important for algebraic geometry in serial representations. And what is very important is this, in this case, we can use a sparse matrix. The sparsity is saved in such a decomposition. The complexity was n cube as previous, and accumulations of errors is not so good as for PLQ, because the leading elements cannot be changed. So we cannot try to take the biggest pivot element. The next variant of LU decomposition was LEU. It was appeared in 2010. What is the difference? It was the first algorithm with complexity of matrix multiplications. It was block recursive algorithm, and it's good for sparse matrix. We call it the fast generalized Breuer decomposition, because it is more faster, because it can be done the decomposition not for the full rank matrix A, but not full rank matrix, as for in this example. And now the matrix L is low triangular, you see it here. U is upper triangular, and E is matrix of permutation. And what is connections between these two decomposition, LU and previous clear Breuer decomposition, is very easy connection, because you can take such matrix J, you can see here, and if you take B equal JA, and then obtain the LU decomposition for the matrix B, then matrix A may be written as the product of three matrices V, W, U, where V is equal L and J L J, W equal J E, and U is the same U it was previously. It was very easy to, if you have LDU decomposition, obtain the Breuer decomposition and back. This is first algorithm that can be done, can be used for the case of the domain. A little, some words about the notation, because it is very important. Let we have matrix A. Matrix A with elements little a ij of size n by m over the commutative domain R. And we will use such notation. This is submatrix of the matrix A, which consists of the corner block. This corner block situated in the left upper corner. It's size chi-1 by chi-1, and we surround it with one row number I and column number J. And we say that this is a surround matrix, and the determinant of this matrix we call the surrounded minor. The minor that is surround this corner chi-1 by the I row and J columns. And what is important for the first LDO algorithm is that we take the case when all the elements which stand on the diagonal of this initial matrix. This is corner minors, where AKKK is upper left corner minus, which has size k by k. We say that each such corner minus must be not equal 0. In this case, we can do such factorization. The matrix A will be equal product of three matrices LDU, where L is such low triangular, U such upper triangular, and this is the diagonal matrices. What you can see here, each element is not some abstract element. Each element is indeed minor. This is the same minor that we have here. It was notation, and the element A chi j, you can see here in each places the same minors you can see. Such decomposition can be done absolutely exactly if you want. You can obtain it. And what is new features? These decompositions can be calculated without errors. This is the first. The complexity is n cube, not suitable for sparse matrix as for previous. If the we have now one restrictions: the diagonal minors must not be 0. And if you, what about arrows? If you calculate with rounding, then you can get a larger error than in PLQ factorization, because you must take absolutely exactly the same element that you take in the main diagonal. The main idea to change this algorithm for new algorithm, where we obtain here not diagonal matrix but some other, and we can use we can do permutations. We can do strong permutations. So it's another variant of LDU is P LDU Q. And now we do the same as we do with standard LDU decomposition. It's very similar, but we can change the notations. If we do permutations, rows and columns, and we obtain the matrix P and Q, P is for permutation of the rows, Q for permutation for the columns, then at the end we can construct such matrix A prime, and then all the minors, alpha ijk, is a minus of this I prime matrices, not for the initial matrices. And then we can write the decomposition in the same form, but we can understand that this is all the elements is minus of this new I prime matrices. And now we start to explain the new algorithm, LSU algorithm that I want to present in this my presentation. It's the same as previous. We can work in the domain R. This is an example of such presentations, such factorization. Let matrix A, this is matrix A. Then we can do factorization. We call it LSU. L is upper triangular, is absolutely integer. All the elements is in the same domain R. This is upper triangular, all elements in the same domain R. And this is a matrix of permutation, but it's not a clear matrix of permutation. It is a weighted matrix of permutation, and not from the group, but from the semi-group, because it may be not the full rank. What is new features? No, first of all, it can be calculated without errors if you want. Then it's good for sparse matrices. And it has the complexity of matrix multiplication because it is block recursive algorithm. And it has a coarse grained, this is algorithm with good parallelizability. Moreover, we obtain not only LSU decomposition, but we obtain additional matrix M and W. And we obtain the pseudo-inverse, P inverse, for initial matrix A. In the previous example, this is W with integer elements. This is M, and from S we can obtain this about the same matrix S1, and then the inverse matrix for L is equal Sm divided by determinant of A. The same we can obtain inverse for U. Inverse for U equal W S1 divided by determinant of A. And we can obtain inverse matrix. But in the general case, you cannot obtain inverse matrix because the matrix may be not the full rank. So we obtain the pseudo-inverse. The pseudo-inverse has such form: WSM divided by determinant of A in the power 2. In the case when the matrix A is not full rank, this is the determinant of the biggest minors, non-zero minors that you can obtain during the algorithm. And what's the property of this pair inverse? If the matrix A invertible, it would be clear inverse. If it is not invertible, then two identity is true. First, that APA equal A and PAP equal P. So these two identities say for us that it's a pseudo-inverse, but it is not a more Penrose pseudo-inverse because we need more two identities. This more two identities is not, maybe is not correct. And so you can check this, this identity is true. Here it is how we can check it. It is indeed real for this example. It is indeed so. General statement of the problem. We to solve this problem, we must do a little more. What more? We have matrix M given, and let alpha is a determinant of the largest non-generate submatrix located in the upper left corner of matrix A, M. And let A is have size n by n, rank R, and each element of this matrix A is surrounded minors with respect to the minor R. For empty minor, we said that alpha is equal 1. And let this is some sequence of what? Of this is a sequence of non-generate minors. It is nested non-generate minors of the matrix A. The size is R minus 1, and so on. The size is 1. And if we have such sequences, and we want to obtain matrices LU, M, W, all of rank n, and we want to obtain matrix S. It is a weighted permutation matrix of rank R, which has R non-zero elements which equal such product of this determinant. You can see that each element, that non-zero element, the matrix S, must be product of two minors. The biggest minus has the size R, and the biggest element has size determinant of R minus 1, not determinant of R. And we want obtain such matrices with such property. Alpha LSU equal A, LSM equal identity matrix, MWSU equal identity matrix. And we need addition notations. We need obtain matrix E when in the matrix A, after replacing each non-zero elements with 1, then we obtain matrix A. Matrix E is some like matrix of permutations, just element 1 you can see in this matrices. And so we can use the diagonal matrix. If we multiply E by E transpose, we obtain matrix I. If we multiply I transpose E, we obtain another matrix J. And then we subtract from identity matrix J, we obtain J bar J, and subtract from matrix 1, subtract matrix, this is identity matrix minus matrix I, we obtain bar I. We will use all these notations, and together with the notation of the matrix hatted S obtained in the same way, where S bar is the matrix that we can construct from the matrix E. If we, in matrix E, we cross all the non-zero elements, non-zero rows and columns, and the blocks that we can see, we put here the identity blocks, then we obtain the matrix S bar. And if you add S and S bar, you obtain matrix of the full rank. Algorithm. Algorithm is recursive. We denote the algorithm LSU. What is input? Input is matrix A and number alpha. At first step, alpha is equal 1. And we obtain, we want to obtain all these matrices and some minor alpha R, where R is rank of the matrix A. So this is the biggest minors that may be in the matrix A, and it may be several cases. First case is when A is zero matrices. If A is zero matrices, then the result is next. Second variant, when matrix A has size 1 by 1. So matrix A has just one element. This element is not zero, and then the result of the algorithm is the next. And this is the common case when n is greater or equal than 2. Then we can divide matrix in the 4 equal pieces, and we will do 4 steps, 4 recursive steps. First, 3.1 is we take the block A11, and we do also decomposition with this block A11, and we take the number alpha, that was input number, and as a result, we obtain such decomposition. So L11, S11, O11, the product is equal A, and M and W is some kind of inverse matrices for L and O with the property you see in previous slides. Then after it, we compute such blocks using this decomposition. We obtain here, and then we can do next steps number two, number three, with the blocks A21 and A12, which we obtain here. And we all these calculations may be done simultaneously. It's maybe done parallel in parallel form. It is independent one from other. And if we obtain such blocks in this decomposition, then we can compute this additional blocks using the just multiplication operations of the matrix and division by number. As a result, we obtain matrix A22, 3, and we do the fourth steps, recursive steps with matrix A22, 3. This is decomposition. And with using this block, we obtain the new blocks. And this is final result. This is matrix L, lower triangular, we obtain from the obtained previously block. This is matrix U, upper triangular, we obtain from the previous block. This is a matrix of weighted permutations matrix. And to obtain matrices M and W, we can do it easy with such multiplication of the obtained blocks. And this is finished. What is complexity? Complexity is the matrix multiplication, because it is it's clear it is a recursive algorithm to compute how many operations you need for the matrix of the size n by n. Yes, we need 4 times do decomposition of the matrix n divided by 2, and each time we need 29 matrix multiplications. What size? Size of n divided by 2. So we can easy to add each steps the number of such we need such quantity of operation at each steps. This is very easy to compute such geometric progressions and obtain such result. So we see that the complexity of matrix multiplication will be next. What we use here? We use here the complexity of matrix multiplication, m at n. Let it be gamma n in the power beta. Gamma is constant, beta is constant, maybe less than 3. If we use such matrix multiplication, then we put it here, and we put it here, and we obtain the result where you can see 29 gamma n power beta divided by some number. Number is 2 power beta minus 4. Example. This is a full example. We start from the matrix A. We use the first decomposition with upper left block. Here it is 0, 0 to 1 to 0, and the initial element number is 1. This is several steps. The decomposition of this block. Then step number 2, decomposition of the block 21. Here it is. Step number 3, decomposition of the block 12. Here it is. And then we can compute matrix A 2 to 2. And this is step 4, decomposition of this matrix. It's equal 0. So it's very easy to do this composition. And this is a final result, obtaining matrix L, S, U, M, capital M, and capital W. And you can check that is correct. Conclusion. Conclusion is the recommendation for the users. What is the recommendation? If you have a sparse or a dense matrix, and it is well conditioned, and the accumulation of error is not so significant, then the best for you is LU because it is the most quickly. In other cases, when you have a dense matrix and it is not a well conditioned and accumulation of errors is significant, then the classical LU is the best for you. And rest is the best LSU. What is the rest? Sparse or dense matrix. It may be ill conditioned, and no strategy for you gives acceptable solution accuracy. Or another possibility, matrix is over the domain of polynomials or integers and so on. So in this case, for you, the best will be the LSU decomposition. Thank you for your attention, and I'll be glad to answer for your questions if you write me a letter to my email malaschonok@ukmaidua. I'll be glad to answer you for your questions after this conference. Thank you very much once more, and goodbye.
Goodbye.